Okay, so we're going back in time. Actually, we're going forward in time for those of you who are watching this on the video, because this is 2014. So, so what we have coming up next now is a very important concept in Prolog called matching, right? And the first thing that we want to notice here on the slide is that equals is the matching operator. So when you see the symbol here, when you see this symbol, you know, in C++ or Java, we say gets, because this is the assignment operator, and we say this gets this. In Prolog, we're going to say matches. All right? This is the matching operator. So equals is the matching operator. And now, to illustrate how matching works, let's take a look at this example on this slide. The top figure on the slide says triangle, and then it has point, 1, 1, and then for the first argument, and it has A for the second argument, and it has 0.23 for the third argument, right? And then the triangle below it, the figure below it has triangle, and it has a capital X for the left argument. Now, what is capital? Capital means it's what? It's a variable. And then it has 0.4y for the middle argument, and then it has 0.2z for the right argument. And what we're going to do is we are going to see how this matches, how the top one matches the bottom one. And so here, the caption of figure 2.7 says, matching triangle 0.11, A, 0.23, and then match triangle X, 0.4Y, 0.2Z. Now watch this. We're going to, well, let's demo this and see if you can anticipate what this is. Okay, so here's our demo, and what we've done is we have set up the text of that, of the caption of that slide that we were just looking at, and it's triangle 0.11, A, 0.23, and how do we say this? Match triangle X, 0.4Y, 0.2Z. Now here's how the matching works. Watch this before I press return. Does everybody see that this triangle matches this triangle? Are you with me? So that's a good match. And for the first argument, this, what do we have for the first argument on the left-hand side? 0.11. And what do we have for the first argument on the right-hand side? Variable x. So do you think that's a good match? Well, x is a variable, yeah? Okay. So what's going to happen is this x is going to match that. And now what do we have for the second variable here? For the second parameter here? Variable a. And what do we have for the second parameter here? 0.4y. So that, this is a variable, so that will match. And now here we have point here, and that matches this point. Are you with me? And then does this 2 match this 2? Yeah. And then what do we have? And then what else should match corresponding? This 3 should match the variable z. So with all of that in mind, let's see how this matches. Oh, shoot. What did I do wrong? Oh, I haven't consulted. Because triangle, oh wait. No, I shouldn't need to consult. Wait, what did I do? I didn't close the paren?
You need to close the paren for the...
Oh, for this. And now period. Okay. Is that right? Yeah. All right. Phew. It was that easy. Okay. So now does everybody see what happened? This A matched with 0.4y, the X matched with 0.11, and the Z matched with 3. Does everybody see how that worked? Yes.
Now, what if for that first point on the left-hand side it said 0.2, 3? What if the 2 wasn't there? What if it was?
Well, something would have to be there.
What if it was 3 then?
Then it would not have matched. Actually, here, that's a good question. Let's do that. So what you're saying is if this, no wait, which one did you say?
Yeah, that one. If that was the 3, for
Because this 2 matches the last 2. So if this were 3, watch this. No. Oh, that was a good question. So we saw with the demo what happened there. No, because the whole thing has to match. The whole thing has to match. All right? Does everybody see how this works? Okay, so let's do, with that in mind, let's see how matching, let's do a bunch of smaller examples. Suppose we have A, B, C. Match A, B, C. Now, will these match? Yeah, that matches no problem. And if we do A, capital B, C, match A, lowercase b, c. Will this match? Well, we have a no and a yes, so we have a...
I'll split it and say no.
You'll split it and say no? Oh, use the majority rule? Big B is a variable, so what? So how will it match?
Oh, yes, it will.
It will match, and furthermore, what happens? B is, now what do we say? Capital B is instantiated to little b. So you see, it's a variable, and this is what we're talking about here is unification. And what's happening is we are unifying these two things, and they are unifiable. They can be unified as long, and so what Prolog looks for is values of the variables so that everything will match. Do you see what I mean? And it's very sophisticated in in the way it can get the matching to happen. Yeah, did you have a question?
So what is the type, like the B to C?
No types. No types. They're variables.
But the lowercase ones?
Atoms, because it starts with a lowercase. The lowercase a is an atom because it starts with a lowercase. The uppercase b is a variable because it starts with uppercase. Wait, did I say that right? The lowercase, okay. Yeah, question?
So we actually see that, so the equal sign actually has two different meanings there?
No. The equal sign always has one meaning. The equal sign means match. And it either succeeds or it fails.
So the big B equals B isn't instant, it's not saying, what is that saying then?
So the question is, what is it saying? What it's doing is unification will instantiate the variables in such a way that it can match. It tries to instantiate the variables in such a way that it can match. And if big B is instantiated to little b, then these two expressions match.
So the equals means instantiation?
It means match.
Okay, so...
We are matching. We are matching the left-hand side with the right-hand side.
Right, I get the first line. Then the second line comes in that says big B equals...
Well, we're still saying, here's what we're doing. We are asking, under what circumstances can this match?
Oh, if those match.
And if it can be matched, if there are some circumstances when it can be matched, it will search, and it will determine those for which it will search for the instantiations that will make it match. And if it can find an instantiation for which it will match, it succeeds. And it tells you the instantiations that are necessary in order for it to match. That was a good question. Did you have a question?
Well, I was just going to say another way to explain that was if instead of the capital B, you just had like a 3, the number 3 would not match the atom lowercase b, correct?
Correct.
So that would show you, I guess that's another way of explaining.
So yeah, so for example, or if this instead of being a B, let's say this was like a G, all right? So now, will these match?
No.
No, because the G doesn't match. See, it's an atom. See here, if we do G match B, what happens? What happens?
No.
No. If we do big B match B, what happens?
B succeeds.
It succeeds, because if we instantiate big B to little b, they match.
What about B, lowercase b matches?
Oh, good question. Very good question. How about B match uppercase B, right? Like this, right? What do you think? Yeah, either way, on either side. It's symmetric.
What about two lowercase b's?
Okay, what do you mean? Okay, hold on. You mean BB? You mean like this? That's a different one.
What if it's a
No, I think he meant B.
Ha ha! Oh, you guys are asking really good questions. What about capital B match capital C? What do you think?
Yes.
Yeah, why not? Why the heck not? They got maximum flexibility there. Oh, that was a good question.
To itself.
What you mean lowercase b match lowercase b? Well, what do you think? Capital B match capital B. What do you think? Why the heck not? It's just true. Well, it matches itself. A variable matches itself. But any two variables match. Oh, these were good. These were excellent. I was going to demo those, but you guys. So how about this? Check this out. Now let's do capital B, with this in mind, lowercase c, match A, capital D, lowercase c. How about this one? With that in mind, D, yeah. Now you see how it works. You know you can do them with structures, with the structures, and so. But now, so what about A? But of course now the functors have to be the same, right? If we do the same thing that we did before, but this functor is a different functor, right? Then what?
Oh, then no.
No, the functors have to be the same. Do you see what I'm saying? Yeah.
Does the order of the variables have to do with the unification program? Or
Well, the first parameter has to match the first, and the second parameter has to match the second.
The result, it goes D equals D.
Oh yeah. No.
No, it's
So the question is, what about the order in which this one appears? That's irrelevant.
okay.
Yeah. You're just saying that those two variables match. All right. Okay. So here, check this one out. Suppose we do A, B, C, and then this is D, E. Now match this with A. Now what do you think about this? F, G. What do you think? Oh, good for you. F is B. Now you see how that worked? Is everybody clear on this? Here, let's do a complicated one. Let's do, oh, this is going to be hard. A, B, C, D, E, F, comma, G, H, boom, 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 match, A, F, capital F, C, capital I, G, paren, capital J, boom, 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 boom. Well, just peel it apart, right? This is like car, cons, car, cos, C, A, D, 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 R, right? Just peel it apart. Does the functors match?
Yes.
And then what?
And then F.
B, F will match B, and then the C's match, right?
C's match and then I.
Oh, wait. Do I have a different number? Do I have a different number of parameters?
That one only has two parameters.
Yeah.
So
Oh, maybe I typed it wrong.
There should be.
Wait, no, I would get D and then J would get H.
There should be a
the,
parentheses after
the I is inside the C, so the entire C is one parameter.
Yeah, so there should just be a parentheses after I, right?
If that's the case.
Yeah, if you want to put a parentheses after I, then it could.
Oh,
Wait.
no.
Why couldn't I get D?
Wait.
instead?
No, it's fine.
No, yeah, it is fine.
Yeah.
It is fine?
Yeah.
How is it fine?
Just press enter.
Well, no, I want us to figure it out. Just press enter. Come on, give me a break.
Yeah, I is D and then parentheses EF.
J matches H.
Oh,
There's no G.
So you don't need the close.
See how like up there G matches?
the G's match.
And then J and H.
I think this might work.
Yeah, it takes up the whole function thing.
Yeah. Boom. Now look, you guys, think about it. This is what unification does. This is built in. This is the unification algorithm. Yeah? And so it has built into it that, and we're going to take a look at the pseudocode for that in a minute. Okay? So now how about this? How about let's do one that is that feels a little bit more like regular data. Suppose we do date, DM 2001. All right? And we're going to match that date with date D1 May Y1. So
Yeah,
do these dates match?
yeah.
Yes, and how do they match?
D equals D1, M equals May, Y1.
Yeah, M equals May and Y1 is 2001. Is everybody good? See how we can do stuff like that? And then how about this? How about let's do some numbers. A match 5. What do you think? A match 5. What do you think? No. How about X match 5? And what is the match? X equals 5, right? And then how about 5 match X? Okay, good for you. How about X match Y and Y match A? Ha-ha!
X matches A.
X.
Yeah, will it match A or the question is, will X match A or will X match Y?
Both will be A.
Yeah, I think you're right. They are because they are instantiated. Do you understand how that worked? So first X matches Y, but then if Y is instantiated to A, then X is also instantiated to A in order for them to match, right? Does everybody see how that worked? Okay, into the demo. Okay, and now there's some more. Actually, this next slide is kind of interesting too. How would you specify a vertical line segment? What do you know about the coordinates of the points of a vertical line segment? The X is, so see how you would specify it? Point X, Y1 for the other one and point X, Y for the other one, so these X's have to be the same, so that would make it vertical. So how would you check to see if a point is vertical?
Just check that.
Yeah, you would
Will
do,
match. So then point X. Anonymous?
well, a segment has 2 points.
Okay.
So you would say segment, remember a segment had 2 points?
Yeah.
So you'd say segment, and then you'd say point, and then you'd put X as the X coordinate of the first ones, and then Y as Y and Y as the Y coordinate of the second one, and the Y1 as the other one. Anyway,
Why do we need
that wasn't too clear, but
Do we need to check the Y values to make sure they're different?
well,
Otherwise,
otherwise it would be a point. Well, that's a fine detail. So here, let's write down how you would check to see. So to check to see whether the segment is a vertical line segment, you would say seg, and then you would say actually just this. You would say point, capital X, capital Y, and then point, and then X and Y1. Okay, yeah, and then to see, so if you had a way of generating another one and you wanted to check to see if it was vertical, then you would match this one with the other one. Are you with me? And it would succeed if it were vertical, if these were the same.
what do you mean by another one?
Well, you would have to match this segment in order to test to see if this segment,
Vertical or parallel?
Actual value.
no, vertical. In order to check to see if this one over here, to check to check to see if a given segment over here is a vertical segment, you would match it with this. And it would only match if these two were the same, if those two over here were the same. So that's the flavor for how you query to test for these things. Yeah.
How would it match if the Y values are different?
Yeah, so why do the Y values?
Well, all of these are variables. This is a variable, this is a variable, this is a variable. I'm assuming that the thing that you're matching it with has numbers.
But are these not singleton variables then, if we were defining it?
No, they wouldn't be because, Oh, actually, you are right. Haha, singleton. Yeah, actually, what we should do is this. What?
Unless we're,
Singleton. Yeah.
unless we're gonna care if,
Unless we care what that is and we want to know what they are.
well, to make it not a point, not a.
Well, yeah, we could do that. Yeah. Is everybody good? Okay. So now look, here are the rules, and I think you already know these from what we've experienced these all. If S and T, okay, equals is the matching operator. If S and T are constants, then S and T match only if they are the same object. If S is a variable and T is anything, then they match, and S is instantiated to T. We saw that, yeah. Conversely, if T is a variable, then T is instantiated to S. If S and T are structures, then they match only if what? S and T have the same what? Principal functor. Remember we demoed that? If the functors are different, then they don't match. And all their corresponding components match. Notice that this is a recursive definition, right? Because the corresponding components match, but how do the corresponding components match? Well, they match if S and T are blah, 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 So is everybody clear? So that's, yeah, recursive rules. Okay, so now here's some vocab definitions. A clause is a rule or a fact. I think we've used the word clause before. An instance of a clause C is C with each variable substituted by some term. And then comma is conjunction, that's and. Now semicolon is disjunction, and that's or. So it's actually possible, and we will do this occasionally. We will say P if Q or R, where or is this semicolon. But typically, it's more usual for this to be just P if Q and as one rule, and then P if R as another rule, because if this one fails, then it tries this one anyway. So, But we will use this occasionally, all right?
Does this have
The semicolon.
short circuit stuff for conjunction as well, or no?
Oh, that's a good question. If you write it this way, well, is it short circuit? Because it will attempt, when you press if it succeeds because of this, if you press semicolon, it's going to go try the other one anyway. So that's a little, yeah. All right, now, declarative meaning, right? A goal G is true, that is satisfiable or logically follows from the program, if and only if there is a clause C in the program such that there is a clause instance I of C such that A, the head of I, is identical to G, and B, all the goals of the body of I are true. Now, that's a lot of words, but here is an example with a figure that illustrates it. Suppose you have a query, and so you see here the question mark hyphen is our prompt, and suppose we type G period. Then so when will this succeed? When will it succeed? A goal G is true, that is satisfiable or logically follows from the program, if and only if there is a clause C. So does everybody see that this whole thing is the clause, right? Clause in the program. And what is the head of the clause, of this clause? G. And so if that has to be identical to this, are you with me? So this, G has to match this. And then all the goals in the body. So each one of these are goals. So this is the head, this is the body, and these are the goals. Does everybody see how that works? Okay, so now, this is what? The question is how? Now, what did we say when we started this whole paradigm?
We were more focused
On
the what.
and not the how, because the how is built in. But here's the thing. In order for you to write good specifications, you have to understand how it works. Because if you don't, you're liable to wind up with endless loops and inefficient queries. Okay? So it's not 100% you can just be ignorant of how it works. You kind of have to understand that. Are you with me? Even though you don't have to actually write the program, you have to understand how to specify it. knowing how the program works. So in general, what happens is, when you write down your query, what you give it is you give it a goal list. That's your query. And then the program is what's stored that gets compiled. Are you with me? And then in general, what comes out is when you press return on your query, it comes out, if it fails, it just says no, right? And it's not satisfiable. You know, it can't be satisfied. But if it is satisfiable, then it also gives you an instantiation of the variables, what the variables are instantiated to in order for it to succeed. Okay, so check this out. So to illustrate how it does a query, we're going to go through an example where our goal list is the query dark X and big X. So what we want to know is, we want to know what is dark and big. And here is our program in our database. Look what we have. We have big bear, big elephant, and small cat. Are you with me? Or would you agree that elephants are big and cats are small? Okay? And not only that, we have brown bear and black cat and gray elephant. So those are the colors. Are you with me on that? And those are just, what are these? Rules or facts?
Those are facts.
These are facts. Yeah? And then, so far we have these facts. Clause 1, 2, 3, 4, 5, 6 are all facts. Then we have dark Z if what?
Black.
Black Z. Would you agree that dark Z if black? And furthermore, dark Z if what? Brown Z.
And
Okay?
you can put and instead of creating two separate ones, correct?
We could put or instead
or,
of doing
that's
two.
right, that's right.
Yeah. Is everybody with me? Now tell me, before we actually get, and we're going to query dark X and big X, can you tell me, just before we go through, can you tell me which one of the, do we have a dark X and a big, do we have a dark X and X is also big? Do we have something that is both dark and big, do we?
Yes.
What is it? A bear? Okay. Well, let's see how we figure out that bear is dark and big. So here we go. All right. So now everybody sees. Here we have dark X and big X. So the first thing that we are looking for is what? What's the very first thing? It starts on the left. See, here's our query. Dark. So is big dark?
No.
Big dark? Small dark? Dark, dark, dark. Ah! So what does it find? Oops, wrong way. So what does it find? Dark Z. Does everybody see that this dark is this dark? It goes down and finds that dark. Are you with me? And now what happens? Dark Z, but now this is a rule. So what happens? X matches with what?
With the Z.
Z. X, remember, see, look, the dark matches with dark. So what, X matches with the Z, right? Are you with me? So maybe we should say that. So here we say X matches with Z. Are you with me? So now we're going to go through with black Z. Well, they match anyway, right? So, okay. So there's black X, all right? Okay. So now what do? We start, now remember, this is here. You got to kind of remember this here. So now what happens is we start up here, and now what are we looking for? We're looking for, no, we're looking for black. We're looking for black. So what happens? Do we find black? Here's black cat, right? So what happens?
So now X is equal to cat, or X matches cat.
Yeah, X is instantiated to cat. That's exactly what happens. So now what happens is, now did you see what happened here? X is instantiated cat. So now what are we looking for? Oh, but let's go back. So now see, so now we have black X, right? But now X is instantiated cat. So now what are we looking for? Big cat. So now you see our here. Now we're looking for big cat. Well, let's look for big cat. So what happens? So well, big bear. Does that match?
Nope.
Big elephant, does that match? No more bigs. And so what happens? Fail. Are you with me? So now that this fails, now what happens? We backtrack to what? To black cat. Are you with me? So we backtrack to black cat. And so, but now what do we do?
It looks for anything else that could be black.
Yes,
Fails.
and it fails. Okay.
So then it goes back.
So now it black tracks. Yuck yuck. So now it backtracks to dark Z because that's where we got that failure. Are you with me? And now what does it do?
It goes down to the next.
It goes down to dark Z, right? And now what happens? X instantiated to Z. And so now this goal changes, you see. Now it's as if we have brown X comma big X. That's how to think of it. And so now what does it do? It starts up at the beginning again and looks for what? Brown. And here's brown bear. Okay, so now what happens? X is instantiated to bear, and so because X is instantiated to bear, here we go down here, because X is instantiated to bear, now what, the only thing we have to look for is what?
Big bear.
Big bear. And so big bear, and what happens? Big bear and X equals bear, X match bear, and we're done. And you guys, check this out. This is the pseudocode for that algorithm. And it's really not that hard to understand. It's very high level. But this is actually what the unification algorithm is. Yeah, question?
And so that's the how of...
This is the how. And that's under the hood.
Yeah. And the way the way you had the slides, I think that really helps understand how it's working in the process.
Yes.
Because when we first started doing it, I had a hard time understanding how it was backtracking, but this clearly shows how it goes back.
Yeah, yeah. Is everybody... So look, I mean, basically, I mean, we can read through this. It's really... I'm gonna actually run through this even a little bit longer. Okay, it's really interesting. What happens is your program is a list of clauses. Your goal list is a list of goals. You know, like we had those goals, and then our output argument, success, truth value, success will become true if goal list is true with respect to program. Local variables, goal, other goals, satisfied, match, instance, auxiliary functions, empty L, head L, tail. Oh, notice it has a head and a tail, you know, okay, and append, blah blah blah, and then there's a match function that has these items in the parameter list of match, and then here is the algorithm itself: begin, end. If empty goal list, then success gets true. Else begin. Goal gets head of the goal list. Other goals gets the tail of the goal list. That's the car and the cutter. Are you with me? And then satisfied gets false while not satisfied, and more clauses. So there's a loop. And within this loop, there is an execute here. This whole thing, this whole algorithm is called execute. And so the structure of the logic is there is a loop here, and within the loop, there is a recursive call to execute. So it's rather complex. I don't think we've ever done logic like that before. There's actually a loop, and then inside the loop, there's a recursive call to execute inside. That's the structure of the logic. Yeah.
For the goal and other goals, where you have head and tail,
Mm-hmm.
can you explain that just a little bit more? Because I'm a little fuzzy.
Yeah, you know, so the question is about this goal and other goals. Remember, the example that we did, I think, was it like big X, comma, was it dark?
Dark, yeah. I think it might have been the other way, but either way.
Yeah, well, let's say big X, dark X, and let's say smelly.
Okay.
Like you have some skunk. You know, skunks are smelly, something like that. So what would happen is, this is the head, big X is the head, and then all of this is the tail.
And so is there a function that gets the rest of it, or like how does it go down?
Well, yeah. Well, I mean, the question was, what is goal and what are goal and other goals? And the head of the goal list is this one, and the tail of the goal list are these. And so And so other goals is this list. And so when you use other goals, see other goals is used here. When you use these other goals are those other goals that were stripped off over there.
So the tail function does that.
Yes.
Okay.
This is car and cutter.
Okay, so it's a built-in thing.
Well, I mean, the whole thing is programmed in C probably, and so, you know, nothing's built in.
Okay.
But they had to code all it. They had to code it to do that. This is a high-level description, right? So now, that's a really interesting. Now, I would just want to close off by doing one more thing. And this is reordering clauses and goals. Now, here's the thing. Reordering can have a big effect on efficiency, okay? And in an extreme case, if you reorder it incorrectly, you can have an infinite recursion and the thing will not terminate. And we have 3 examples to show you. This one, now remember the ancestor? Remember the ancestor rules?
Yep.
We said this is another version of the ancestor rule. This is called ANC2, which stands for the second version. So ancestor of X is an ancestor of Z if what? X is a parent of Y, and Y is an ancestor of Z. So if we put that rule first, and then if we put this rule second, ancestor of X is Z if X is a parent of Z. So what did we do? We put the base case second. If you put the base case second and your first rule starts like this, it will actually work. But look, if you do this, if you do the ancestor 2, Tom, Pat, it'll try the ancestor first, the ancestor first, the ancestor, and it'll keep trying the ancestor until it fails the ancestor, and then it'll go to the parent, and then it'll finally find the parent, and then it'll go back and do the ancestor. See? But it'll work, but it will be inefficient. Right? Now here's another option. Now this might be closer to what we did. This one has the parent first, the base case first. This is ancestor 3. Are you with me? So the base case is still first, but what's different about this one compared to what we did before? The recursive one. I think before we said parent YZ, comma, ancestor XY. So what we did is we switched these 2 around. I think these 2 were switched around in our original.
Yeah.
Well, this will still work. And it's a lot more efficient than the previous one. But here, can you see that this one is endless? Because what is it doing? It's starting with ancestor of XZ if ancestor of XY. And so ancestor will keep calling ancestor, which will keep calling ancestor, which will keep calling ancestor, and it will keep calling itself over and over again, and it will be endless. Do you see? So this is an extreme case where you actually have an infinite execution trace because of the ordering of these goals. The bad ordering of the goals.
Order really matters.
Order is really crucial. And so you can't just, even though we say, oh, well, you don't have to worry how, well, you do have to worry how when it comes to ordering your goals. So you have to understand how the engine works. It's not, they're not completely divorced. Good deal. See you next time.